Hello grade 9s, this is Mr. Miller and welcome to lesson 4.3 on similar triangles. First, what are similar triangles? Similar triangles are triangles that aren't necessarily the same size. One can be enlarged compared to the other one or reduced compared to the other one. But they have corresponding angles that are equal. That's one thing we're going to look at, corresponding angles that are equal. Also, corresponding sides that maintain a constant ratio between them. So we'll be looking at corresponding sides and taking a look at the ratio between their side lengths. So for the first example here, it says to list the corresponding angles and the corresponding sides in each pair of triangles. For part A, I'm assuming that the orientation of triangle DEF is the same as the orientation for triangle PQR, so that the angle at D is equal to the angle at P, and the angle at E is equal to the angle at Q, and the angle at F is equal to the angle at R. Now some people prefer to specify, for instance, this angle at D here by calling it angle EDF. There's nothing wrong with that, but I just prefer this shorter notation. It certainly does the trick. The other thing to notice is that since I'm calling this angle D up here, I'm going to call this side length directly opposite it the side length D, but I'm going to use a lowercase letter, lowercase d. And I know some people are going to say, well, that side length should be called EF because it's the length from E to F. That's true, that's another way to specify it, but this way is fairly easy. So you can see how I've done my labeling, right? Lowercase e across from uppercase E, lowercase f across from uppercase F, and the same thing is true on the other triangle. P, Q, and R across from P, Q, and R. So that means that the corresponding sides, while the corresponding angles are equal, the corresponding sides are not equal. So for instance, that side length D might be something like 2 times the size of P. And if that were true, then it means that E is going to be 2 times the size of Q, and F is going to be 2 times the size of R. So that's how the corresponding sides work. There's always a constant ratio between them. I may be a little bit off, it may not be exactly 2, but you get the idea. It's always the same number that multiplies them. So now let's take a look at part B. In part B we've got triangle MNO and triangle FGH, and you can see fairly clearly that we have 2 right angles, so obviously those are equal to each other. This angle is the smallest angle, it's across from the smallest side, so I know it's equal to the angle at H here, which is across from the lowercase h is across from the smallest side on that triangle. So I've labeled the 2 smallest angles equal to each other, the middle angle equal from both, and of course the right angles are equal to each other. So based on that labeling, we can say that angle N is equal to angle G. It's the largest angle, 90 degrees. The second largest angle is O, which is equal to the angle at F. And angle M is equal to angle H. And so now that we know the corresponding angles that are equal to each other, we can talk about the corresponding sides. So the side length N, which is the hypotenuse of the larger triangle, may be something like 2.5 times the size of the hypotenuse of the other triangle, G. So if that were the ratio, and I don't know, I haven't measured it, but if N is 2.5 times the size of G, then that means that O is going to be 2.5 times the size of F, and M is going to be 2.5 times the size of H. So that's how the corresponding sides work. Let's take a look at two triangles and try to figure out if they're similar. Now, let's suppose you didn't know whether these angles were equal. Okay? How could you figure out if these two triangles are similar to each other? So what you can do is start with the largest side of one and compare it with the largest side of the other. So the 10.5 divided by 3.5 is 3. Now take the second largest side of one and compare it with the second largest side of the other. You notice that you're going to get the same number in this case. If you didn't, they wouldn't be similar, but it looks like so far they are similar. Now take a look at the shortest side length of the larger triangle and the shortest side length of the smaller triangle, and that ratio is still maintained at 3. So here's the conclusion that we can draw from that. Since there's a constant ratio between corresponding side lengths, that means that these two triangles are similar. So yes, it is true that this angle is equal to that angle, and this angle is equal to that one, and this angle is equal to that angle. And you notice I'm making symbols to show that they're matching. A similarity statement goes like this: triangle something 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 similar to triangle. We've got to specify 3 other vertices. Now you have to be sure that you get the order right. So if I say BCD here, if I start with B as the first vertex, you must start with R as the first vertex for the other triangle, because they have the same angle at that vertex. Okay, so it's nothing to do with alphabetical order. That could be mixed up in a different example. The angle at C matches the angle at S, and finally the angle at D matches the angle at T. And just so you remember when you take a look at your notes later, that symbol is to be read as is similar to. So this reads, triangle BCD is similar to triangle RST. Okay, let's take a look at some numerical examples now. We're given that triangle MNO is similar to triangle MPR. So obviously the M and the M are the same. They're both right angles. So the P and N go together. So P and N have the same angle. Okay. So I'll put little check marks for both of those. And we also know that O and R are corresponding to each other. So now, since we know that, we know that they're similar, we know that there is a constant ratio that multiplies the smaller triangle to get the larger triangle. So for instance, if I look at the hypotenuse of the smaller one, 7.2, and I multiply by some scale factor, this is going to give me the 13.68. So if you want to know what is that scale factor, you're going to have to do a division to figure that out. And so that 13.68 divided by 7.2 is equal to 1.9. So that's the scale factor that we're going to multiply by. Now, since we want to know x, which is across from that check-marked angle, we need to go across from the check-marked angle here and look at 4. And we need to take that 4 and multiply by 1.9. That's going to give us x. So now 1.9 times 4 gives me 7.6 units, and that is the missing length we're trying to find. So this is one way to do it. The other way to do it is using proportions. So if you prefer, you can do it this way. You can say the ratio 13.68 over 7.2 should be equal to the ratio x over 4, because those are corresponding sides. So to get x, you can do 4 times 13.68 and divided by 7.2. You're still going to get the same answer of 7.6 units. You've just shown your work a little bit differently. It's up to you whether you prefer method 1 or 2. You can just copy down one of those two if you like. So now let's take a look at another example. It's a little bit more tricky. In this one, what I've done is I've separated this triangle onto one side and this triangle onto another side of the page. And the reason I've done that is because here we have that we've got two vertical supports on a ramp that form two triangles. Triangle ABC is similar to triangle DEC, but they're overlapping and it can be confusing. So separate them out. It's a little bit easier to figure out your work. We want to find the height of the ramp by calculating the missing length y. And of course we want to show our work. So triangle ABC is bigger than triangle DEC. That 5 meter side length you can get by taking the 3 meters and multiplying by some scale factor. So what is that scale factor? Well, it's going to be 5 divided by 3, which is 1 2/3, or you can write it as 1.6 repeated. It doesn't matter. It's all the same. To get y, you know that y is the side length that's across from this angle, and the corresponding side length here is 1.5. So you need to take 1.5 meters and multiply that by 1.6 repeated or 5/3, whatever. It'll all give you the same answer. 1.5 times 5 divided by 3, that's equal to 2.5 meters. That's the height of this ramp. Now that's one way to do it. The other way to do it is, like I said, using proportions. So you say the big side length over the small corresponding side length, that's 5 over 3, is equal to the large height over the small height. Those are corresponding side lengths. And so to get y, you can do cross multiplying and dividing by the third number in the proportion. This will still give you the same answer of 2.5 meters, but again, you're showing your work in a different way. So that's it. Here's your assignment, and thank you for watching this video.